Good morning, team. Chemistry coach coming at you. We're getting into some of the good stuff in kinetics today. So we're going to delve into this realm called integrated rate equations. We've looked at rates and rate constants and the method of initial rates and reaction order and all that fun stuff. But ultimately, what we want to look at is, can we find some equation, some mathematical equation that can allow us to calculate the concentration of some species after a certain amount of time has elapsed, or how long would it take for the concentration of some reactant to drop from this starting value to this value at some point along the reaction path at whatever time that is. That would be pretty cool if we could do that, right? The predictive power would be amazing. Well, guess what? We can. They're called integrated rate laws. We're going to take the rate laws and we're going to do 0th order, 1st order, and 2nd order only. If you want to go to higher orders than that, we're not going to do that. I won't be doing that in general chemistry. You can take grad school or maybe in PChem or something where you can do, pseudo, take a 3rd order reaction and make it into a pseudo 2nd order or something like that. I'm not going to cover that kind of stuff, right? You can read about it, have some fun, but you can do that at a higher level. So we're going to just do 0th order in this video, 1st order in the next video, and 2nd order in the 3rd video on that, and look at what are called integrated rate equations. Ooh, integrated. Did you say integral? Do you mean calculus? No, not calculus. This isn't a calculus-based class, but I'll put enough in there to satisfy my mathematic-minded calculus friends out there watching this. But if you haven't taken calculus or have no interest in calculus, you can just skip the little tiny bit of calculus that I will throw on here. And all you have to worry about is the final integrated rate equation, which I'll provide you. At least in my class, I provide you those on exams. So let's start with 0. We'll just go in order, 0, 1, 2, get progressively, more challenging. So let's kind of review if we have a 0 order reaction. So let's just take this general equation, right? So we've got some reactant A with some balanced, stoichiometric coefficient going to whatever the products are. Of course, if you're dealing with a problem, you'll probably get some more specific information. We can write the rate law for that, okay? If it is a 0 order reaction, then we know it's going to be 0. That superscript is going to be, or that exponent part is going to be 0. So we're going to have the rate of that reaction is equal to the rate constant times the concentration of that reactant, since we only have one reactant, raised to the power of 0 if it's 0th order. And of course, anything raised to the power of 0 is just 1, so that's just the rate constant. So the concentration term just drops out. That's kind of nice, right? Well, remember what rate is. We talked about that in the beginning of our kinetics journey here. It's just negative because it's a reactant that's going down. 1 over the stoichiometric coefficient, which is A, which is usually going to be 1 in most scenarios, times the change in the concentration of A over the change in time, right? We saw this from the graphs we were doing, and that will equal K. So I'm just substituting that mess in for R. Well, we've got this changing term, right, in the concentration of A and a changing term in the concentration of T. So final concentration of A minus initial concentration of A, final time minus initial time. Well, let's separate those terms out. Let's put the changing concentration on this side. Oh, and my calculus friends, differentials maybe. So let's isolate that term. Let's move the negative sign over to the right. This constant A over to the right, which is the stoichiometric coefficient. So the change in A will just be negative A times the rate constant. Those are both constants. Times the change in time. So I've separated those delta terms, or if you're in calculus, you put a little d there, I think. It's been like over 3 decades since I've taken calculus. Okay, so if you want to read, I'm not going to go to the gory details, but you can review it. What we're going to do is integrate both sides. We're going to put a little integral there, going from the initial concentration A to the final concentration of A. A little integral here from initial time to final time. So I feel like I was talking like Cartman there. Initial time to final time, kitty, tizzy poofs. Just random things go through your brain. It's amazing. If you are into calculus, go ahead and do that for me, right? Integrate both sides and see what you end up with. That's called an integrated rate equation. Obviously, I'm out of board space, so let me pause this and I will do that. Now, what I'm going to do on the next board is not required for my class. I'm just going to do that to satiate my calculus watchers. Let's integrate this. As the garbage trucks are going outside making noise, and the gardeners over there and the neighbors and my kids are doing piano lessons downstairs, we'll work with all of that. I don't know if that's going to trickle in behind you, but again, all of this is not required for my class. It's only just to satiate those who want to jump down the rabbit hole a little more. Or if you're into calculus, you probably actually, if you're taking calculus, you probably know better than I do right now. Remember, I took calculus probably way before you were born. But and this is for zero order reactions, so I rewrote that equation, right? So we've got the delta A equals negative AK delta T. And let's put the little integration, the integral in there. And we're going to go from the initial concentration to the final concentration on that side. And from 0, T equals initial time, we'll just call that 0, to some time in the future. All right? Boom. Pop those integral signs in there. Well, this is a constant, right? That's the stoichiometric coefficient, which is commonly 1. So a lot of times you see this, they don't even use the A. It's just assumed to be 1. Okay, no big deal. The rate constant's a constant, so we can pull those in front of the integral. So I just rewrote this, pulled the negative AK out, and had the integral of delta T from 0 to T. Now, the delta term, that's what we use in chemistry and calculus. You probably use the D, the differential. So this should look pretty familiar here, right? You got the x to the n dx. In this case, n is equal to 0, right? 0th order. So x to the 0 is just 1. So remember, a to the 0th power from the rate law, that's just 1 anyway. So technically, in this case, we're doing this integral where n is equal to 0 here. Ho-ho! And if you are in calculus, I think that if you do that integral, it's like x to the n plus 1 over n plus 1. Plus some constant c, in this case n is 0. And when we do the subtractions, the constants cancel out. So anyway, you can dig down that rabbit hole all you want. So let's take this integral from initial concentration of A to the final concentration of A. So when you do that integral, just the dx or delta x, you get concentration at time t minus the initial concentration. Yay, okay. Well, over here, you've got the constants out here, and then you'll take the final time, t, minus the initial time. Now, of course, the initial time is 0, so if we plug in 0 there, that just cancels out, and you get negative AK times the elapsed time for that. Right? So remember, our goal is to get an equation that relates concentrations over time. This is what we get. So what I did is I moved the initial concentration over to the other side, and you'll see why I do that on the next board. So probably the most common calculation we do is, okay, what's the concentration of this reactant after a certain amount of time has elapsed? Well, A sub t, that's the concentration, whatever units you have, after some time has elapsed. That will be the negative of the coefficient from the balanced equation times the rate constant, it's important to know that, times the time elapsed, see the negative term, plus the initial concentration. So it's essentially you're taking the initial concentration and reducing it by this factor. So the longer the reaction goes, the lower it's going to be. The larger the rate constant, the lower that's going to be. The larger the stoichiometric coefficient, the larger that reduction is going to be. So the higher this term, right, the lower this answer because that negative sign. It's pretty much just taking the initial concentration plus this correction factor to account for the time that's elapsed, right, the coefficient and the rate constant. That's the integrated rate equation for zero order reactions. Now, what I want to show you is my mathematics people. Right? Remember, we started with these plots, plotting the concentration versus time. So the concentration was in the y-axis. The time was in the x-axis. Y equals mx plus b. Oh, let's do that on the next board. And we can actually make, if you have y equals mx plus b, we can do a graph from that, a plot, which should give us a straight line. And if we do a least squares fit, we can get the slope and the y-intercept. Oh, let's do that. Here we go. You ready? So this is the integrated rate equation for zero order reactions. The concentration of time t of the reactant is negative AKT plus the initial concentration. Y equals mx plus b. We love straight lines in chemistry. So if the concentration of that reactant is y, And the other variable, right, everything else is a constant, is the time, that's x. If I plot the concentration in the y-axis versus time in the x-axis, I should get a straight line, right? You can actually do this on Microsoft Excel or with a hand plot, and you'll get that negative sloped straight line. You can do a least squares fit, pop it in there, right? Insert a trend line, all that fun stuff. And then the computer can calculate the slope and the y-intercept for you. Of course, y equals mx plus b, the y-intercept should be the initial concentration right there. Boop! At time equals 0, it's the initial concentration of A, yay! And then the slope is all this junk in front of the variable t, negative ak, right? So the slope m will be negative the stoichiometric coefficient times the rate constant. Note the negative slope. So from the slope of a least squares fit of a plot of concentration versus time for a zero-order reaction, you can get the rate constant from that. Well, we might be doing that in lab. So if you just take the slope, right, change the sign on the slope because it's going to be a negative slope, right? So the negatives will cancel out. Divide that by the stoichiometric coefficient, which is commonly 1. You've got the rate constant. Yeah, okay. And we can look at the units of the rate constant from this, right? Slope's going to be delta y over delta x. So we can get the units on that. Do the least squares fit, right? So let me erase this. And let's look at the units on the rate constant. Slope will be the change in the y-axis over the change in the x-axis. So it would be units of the y-axis, molarity, or a concentration, whatever it is, over units of the x-axis, which is time. In this case, I have seconds on here. So units on K will be concentration over time, right? So whatever the concentration unit, whatever the time. So if you plotted this in minutes, it'd be over minutes. That's one way you can recognize the zero-order reaction is by, if you know the rate constant, you just look at the units. If it's concentration over time, boom, you know you got a zero-order reaction. Another way is if you plot concentration data versus time and do a least squares fit and you get a straight line, right? Do the least squares fit on that. If you see that straight line with a negative slope, you know it's a zero-order reaction. That's not going to be a straight line if you plot concentration versus time for first or second order. We're going to have to plot a different variable versus time, as we'll see, as the result from the integration turns out. All right, pretty cool. This is a really great way. Hard to do on an exam, but great in lab and homeworks where I give you data, concentration versus time data, and you do an Excel plot. We're going to do that in my class. All right. So boom, that's how you can determine 2 ways to determine zero-order equations. Units on the rate constant or plot concentration versus time and see if you get a straight line. Let's do one example using this equation here. Most of the time you're going to solve for the concentration after a certain amount of time's elapsed. So you'll be provided the initial concentration, the rate constant, you'll have the stoichiometric coefficient, and the time elapsed. Or we can flip that around and say, well, how long would it take, solve for t, for some initial concentration to drop down to some final concentration, right? Or I could say, hey, it takes a certain amount of time for this species to drop from this concentration to this concentration. What's the rate constant? So 3 kind of things. So I'll do that throughout these next 3 videos. I'll do one for 0, one for first, and one for second order. One of them will solve for the final concentration. The other will solve for the time elapsed to get to a certain concentration. And one of them will solve for K. It's just a math equation. That's all kinetics really is. What equation do I use? Plug in the numbers. I'll give you every variable except one. The key is what order. Your first step is always going to be what's the order of the reaction, because that will tell you which integrated rate equation to use, because they're going to be different for 0, first, and second. We're just doing 0. So let's do one example of 0 order, and then we'll do first order on the next video. Ready? So this is kind of the approach you're going to do for all kinetics types problems that use integrated rate equations. You're going to look at the problem, and it's usually it's like thermodynamics sometimes. It's like, where do I start? Or gas laws, if you haven't done thermodynamics yet, right? Which equation do I use? Once you've figured out the equation you're using, I'll provide you all the variables except one, and it's just a math problem from that point, right? With algebra. Same thing with kinetics. What equation do I use? Well, you don't know which equation to use unless you know what order that reaction is, 0, 1, or 2. It's one of 3 options. Don't guess. It's either going to be stated in the problem, it's a first, second, or 0 order reaction, or you'll be provided enough information to discern that. I like those ones, right? Maybe you'll even have to make a plot and see if you get a straight line plotting, some concentration versus time or something. Well, let's say we got this reaction, A going to products. Let's do a generic one. If the reaction is a rate constant of 3.10 times 10 to minus 4th molar per second, how long, solving for T, will it take to reduce the concentration of A from 0.95 molar, that'll be the initial concentration, to 0.18 molar. That'll be the final concentration, A sub T, right? So we've got everything we need. We're solving for time, but we need to know which equation to use. Oh, it doesn't tell you if it's, well, you kind of probably figured out a zero order because that's this whole video, right? But let's say you're on an exam and it could be 0 first or second. You don't know. And it's not stated. First thing you want to do is look for the rate constant. If the rate constant is provided, look at the units of the rate constant. The units on the rate constant is concentration over time. That's always going to be a zero order reaction. Memorize that, right? Zero order reactions have a rate constant with units of concentration over time. This happens to be molarity per second. Boom! We have identified the reaction order, zero order. So now, hopefully now either your professor is going to make you memorize the integrated rate equation, or in my case, I provided for you. Now we know what equation to use. Let's plug the data into that rate equation, and we should have everything except T. If you're on top of it, go ahead and do that before I do the next board, but I'm going to pop the integrated rate equation on the next board, and let's isolate the variable T, solve for T. Now, it doesn't say how long it would take, right? So let's just put, now if it's not specified in the problem, you can do whatever units you want. How long would it take? Let's do that in minutes, okay? Just for kicks and giggles. That way, I try to do that when I make tests. I try to be a little more specific rather than saying what mass or what time, because it's vague on what the units are. So you can get a whole bunch of different answers and it's like, it's a pain in the butt to grade. So if I'm more specific like that, and that I don't always catch it because we always make assumptions, right? But if I say in minutes, now everybody's going to have the same answer and hopefully the same right answer, but they all should have minutes in there. So go ahead and calculate T in minutes, write up that integrated rate equation, plug in the variable, solve for T. Do that for me real quick. I'll be right back. All right, I'm rushing this one. I got to take my daughter to sewing lessons. Here we go. We got 1 minute left on the test. Go. We know it's zero order. Concentration at time T is negative AKT plus the initial concentration. I know the initial concentration that was provided. I know the final concentration that was provided. I know A, that's equal to 1 from the equation provided. I know K, that was provided. Solve for T. So T will be the final concentration minus the initial concentration divided by negative AK. Let's plug them in. Now we got to do the subtraction first to track uncertainty. So that'll be 0.18 molar minus 0.95 molar over negative 1, A is 1, times the rate constant, 3.10 times 10 minus 4th molarity per second. All right, well, to track, we got to do this in 2 steps to track uncertainty. So let's do the subtraction, limited to the hundredths place, 2 decimal places. So 0.18 minus 0.95 is going to be negative 0.77 molar. Okay, over negative A is 1. Now, I'm rewriting the rate constant into a dimensional analysis, right? Because I want to see the units. So I'm going to go 3.10 times 10 minus 4 is molar per second. I just take that second into minus 1 and flip that up in the numerator. And now I can see the molarity cancel. And I asked for this in minutes, so there's 60 seconds per minute. I can see the seconds cancel out, and I get minutes up in the numerator. All right, don't technically have to do that, but that way I know I've got everything correctly in the numerator versus denominator. So that 60 is exact, 3 sig figs there, the 1's exact, 2 sig figs there. I'm good at 2 sig figs. I get 41.39 minutes. Good to 2 sig figs. 41 minutes. Takes 41 minutes to drop it from 0.95 to 0.18 molar. Let's do first order in the next video. I'll be right back after I drop my daughter off. Yeah!